Hello everyone. Today we'll be talking about the dual purpose deep perceptual hashing algorithms. I'm Shubham Jain from Imperial College London. Perceptual hashing based client-side scanning, or PHCSS, is being proposed as a solution to detect illegal content by companies like Apple on end-to-end encrypted platforms like iMessage, WhatsApp, Signal, etc. At the same time, governments in the UK and EU are working on legislations that will mandate the installation of this technology on hundreds of millions of devices. Aim of perceptual hashing based CSS or PHCSS is to detect the copies of images which are known illegal content. So the proponents of this technology, they claim that it has limited capabilities. It can do only one thing, that is detect copies of known illegal content and nothing more. So what does this mean is that let's consider that we have this database of illegal images. Let's assume we are in a world where cute dog images are illegal. So we have this dog, an image of Oscar. And then I want to send an edited version of this image to a friend. And this here, the image that I'm sending is a cropped, rotated, and after applying a sepia filter to the image. So this image shall be detected as an image copy. But now there's another image of Oscar. And this should not be detected as illegal content because this is not a copy of the image in the database. And similarly, any other dog image shall not also be detected as Oscar, shall not be detected as illegal content. And this is what they mean, is that it can only detect if an image being sent is a copy of known illegal images, and it cannot detect if two different looking images share the same entity or component. But what we show in this work is that we can actually build PHCSS or this technology with a secondary purpose, where we show the secondary purpose to be facial recognition of some target individuals. We show that this secondary purpose is hidden. That is, it cannot be detected by some auditors. And then taken together, our results show that this technology itself can turn millions of personal devices into tools of surveillance. And to understand our contribution, let's first understand what is perceptual hashing and how it works. So this is a technology that is being used since a decade and more for image copy detection. That is to check if two images are copies of each other. And this copies could either be edited or exact duplicates. And for doing this, the way it works is that it converts an image to a fingerprint such that two similar images have similar fingerprints. And currently, state-of-the-art perceptual hashing algorithms are generally based on deep learning-based neural networks. For example, Apple's neural hash, which was proposed in 2021. So let's say I have this database of known illegal content. And first, the way this works is that this data is converted into fingerprints for each illegal image. And then if I want to send an image to a friend, there will be a perceptual hashing algorithm that will be deployed on device. It will convert the image into a fingerprint. And this fingerprint will then be checked against fingerprints in the database. And there is a use of a threshold T, that if the distance between any fingerprint in the database and the fingerprint of the image I'm sending is less than T, then this is flagged as a match. And if it is flagged as a match, then a raw or unencrypted image can be shared with the third parties, with the law enforcement agencies or for second review, and some further action will be taken. And if no match is found, then the image is encrypted as usual, and it is sent to your recipient. So going back to the idea of limited capabilities, here I think we have developed a small visual guide to explain our contribution. So here is a database of illegal content, where instead of fingerprint, we show you the image or actual images that have been derived. And the yellow circles denote the image in the database. So let's say if I have any other image that I want to send, this image should be very closer to the image in the database, while any other image should be very far away and should not lead to any flag match. So the question that we are asking is that the perceptual hashing, that how can we build PHCSS with a hidden secondary purpose that will enable surveillance? So we consider our attacker to be an organization. It could be a government or a company who is providing the perceptual hashing algorithm. The aim of this attacker is to use this technology for facial recognition of target individual, For the sake of presentation, let's assume I am the target individual that they want to detect. And they want to detect new or previously unseen images of me. And furthermore, the attacker wants to keep this feature hidden. What this means is that this technology will be deployed on our devices. So it's imperative to assume that there will be auditors who will take the algorithm, take the database of fingerprints, and try to see what are its capabilities, what they can do. And they shall not be able to detect that this technology has been built with the facial recognition of some target individuals. And to achieve these aims, they have the ability to provide and develop the perceptual hashing algorithms. They have access to some images of target individual, that is me. And finally, they can also add some images to the database. But these images can be visually verified by a third party, for example, like charities like NECMEC and WFF. So to build this dual-purpose perceptual hashing algorithm, we train a state-of-the-art algorithm with a modified training objective. In each iteration, we construct a batch of images using a primary data set and a secondary data set. Primary data set is used for the primary task of image copy detection. Secondary data set is for secondary task of facial recognition of target individual. We have some task-specific augmentations that we apply. It goes to the network. We use contrastive loss with cross-batch memory. It takes it, constructs the two different losses for both the tasks, and the final loss is computed using the weighted sum. And finally, we use a DIS21 dataset for our primary task. It has been specifically designed for image copy detection, and VGG phase 2 dataset for secondary task. Again, there are a lot more nuances and details. The whole process has been designed such that it does both the primary task and the secondary task, and the secondary task remains hidden. So going to the results. So for evaluation, we consider a baseline as single-purpose model, which are basically the models that are designed to do only on the primary task of image copy detection. And for evaluation, we send a set of query images to match against a set of database images in different scenarios, and we see how the model performs. So first task is performance on primary task of image copy detection. Here, we have a database, which is like 1 million images in the database. And we have about 25,000 query images, of which some of them have a match in the database, some of them don't. What we see here is that our single-purpose model, which can only do image copy detection, has similar performance to dual-purpose model. So we don't see any loss in performance on the primary task. Then we look at the performance on facial recognition of target individual. So for this, we have database which contains known images of target individual that the attacker has access to. And some query images contain new images of the target individual as well as images of non-target individuals. So here we see the recall. It goes up from 1.2. Like basically, a single-purpose model can flag 1 out of 80 images, while our dual-purpose model can flag every 2 out of 3 images that they see of the new images of the target individual, which means it is very reliable when it comes to doing facial recognition of target individual. We see the precision also goes up. It goes like, and what this shows is that our model is not flagging every face it sees in an image, which means it is not a general face detection algorithm. Similarly, but someone can ask that, oh, you are matching against the known images of target individual, that's why it's not matching, but you can always, maybe it could be a general face recognition algorithm. So we do this we take known images of a non-target individual X, and we take new images of this non-target individual X and see, does our model have a general face recognition capability? And what we see is that it doesn't. The recall and event score for the single-purpose and dual-purpose models are similar, which shows both of them are terrible when it comes to doing general face recognition. But the precision for the dual-purpose model is high. It is because it flags fewer true positives, but also flags fewer false positives on non-target individuals. Finally, what we see now is that we have a model that does this dual purpose, which has a secondary purpose now, which is facial recognition of target individual. And at the same time, it also does its primary task of image copy detection. But now to enable it in the actual system, we need to add the known images to the database, which means I need to add known images of target individual, that is mine, to a database of illegal content. But a third party like NECMEC, who will be auditing this database, can always verify that, oh, I don't really look like cute dog. So this could be flagged. So how do we do that? And for this, we use the previous work of collision attacks, where we take the fingerprint of the known illegal images. We evaluate a mean. We call this a template hash. Then we take an illegal-looking image, a cute dog image, and we apply a minimal perturbation such that the image is modified and it has similar hash as a template hash, but visually it still looks like a illegal image. And this is what our results look like. You have this target individual, and for which, on the right-hand side, you have the original image, which was very far from the target individual in terms of distance using for the fingerprints. But we modified it with a minimal noise such that in the center, you see that the image that is being added to the database. So now, when an authority like NCMEC looks at this fingerprint, looks at this image, they will be like, OK, this looks like a cute dog image, looks illegal. Fine. To conclude this talk, I think what we show here is that we can build a dual-purpose perceptual hashing algorithm that does both the secondary task of facial recognition of target individuals on top of its primary purpose of image copy detection. We show that an auditor who has access to this perceptual hashing algorithm and database of fingerprints will observe that the performance of the algorithm is equivalent to any state-of-the-art perceptual hashing algorithm on the primary task. They will observe that this is not a facial recognition algorithm, and they will also observe that this is not a general facial detection algorithm. Furthermore, organizations like NCMEC, who will be auditing the database, will not observe any malicious change in the database, malicious additions. So to conclude, proponents of PHCSS, like Ofcom, they have claimed that in their report on perceptual hashing algorithms that it's a technology with limited capability. But we here show that it can be built with a hidden malicious secondary purpose without compromising the performance on primary task. Our research shows that we don't completely understand the capabilities of technology, of these tools. And here we have shown one way on how this can be abused. What we assume is that more research is needed to understand the capabilities of technology. And we hope this will provide an evidence to legislators and policymakers in the further debates on the topic. We'll provide a lot more analysis in our paper, and thank you.
Do we have any questions from the floor? Sure.
Hi, thank you. Super interesting. I guess I'm curious, on the slide you mentioned, you sort of tuned the precision of the primary purpose to a particular thing and then measured the precision of the secondary purpose afterward. If you change the threshold of the precision of the primary purpose, how does the threshold of the secondary purpose change?
Yes, so we provide the results in the paper. What we see is that as you increase the threshold, for example, here we consider a threshold with precision of 90. But if you increase the threshold with a higher precision, you can go up to 95, 99. We see our recall doesn't change much. And the precision on the facial recognition, it only improves, while the primary task performance on both the things remains similar.
Thank you.
Okay, and we have one more question.
Matt Wright, Rochester Institute of Technology. Nice talk. Looking forward to some of the future steps, do you think that it would be possible to have, just with more monitoring and auditing of more steps in the process, to something that could actually be only single purpose?
It depends on who defines that monitoring and where does it come from. But at the same time, I think all the steps, more advanced methods can be developed such that it could bypass those detection mechanisms. What will probably be an absolute solution to this particular attack is that if the models are reproducible, which means whoever developed these models, they have to release the training data set, the training mechanism, make it completely auditable, which will allow people to actually see that, oh, how are these created? And this kind of investigations will probably help in detecting these mechanisms, but asking for reproducibility, I think, is probably something that is not realistic.
Thanks.
Okay, thanks again to Shubham
Thank you.